Okay, thanks, Richard, for this introduction, and thanks to the organizers for inviting me, and also congratulations to the prize winners today. We'll hear more about their work later. So I'm going to talk about cycles on the moduli space of abelian varieties, and one advantage of speaking in the afternoon is that some of these topics have been introduced before. There was a beautiful introduction to Shimura varieties in Anna Kariani's talk, and the moduli space of abelian varieties I'm going to talk about is an example of one. But nevertheless, I will give, if you've forgotten from the morning, I'll give a short introduction to the space, and it will be from a rather different perspective. In fact, I'm going to be talking in some sense about, well, not exactly cohomology, but the algebraic cycle theory, which is it's close to thinking about cohomology. And Anna's talk was also in some sense about cohomology of related objects. And you'll have to judge whether these are like two ships passing in the night, or they're related, or we can discuss that later. OK, so the objects are abelian varieties. That the objects, the moduli space parameterizes are abelian varieties. And you can think of this as a complex torus. So that's C to the G. G will be the dimension of the abelian variety. And such an object is made by taking this vector space, and you quotient by lattice. And the lattice has a special form because you want the complex torus to be an algebraic variety. And the most concrete way to think about this form is that I have to give 2G vectors that generate this lattice, and the first G of them are just the basis vectors, and the last G come from the columns of a symmetric matrix tau with positive definite imaginary part. That's what one of these abelian varieties looks like. And then if you want the moduli space, if you're in dimension 1, that's the upper half space. And for a higher dimension, it generalizes the Siegel upper half space, which is the space of symmetric matrices with positive definite imaginary part. And the most concrete way to think about this moduli space of principally polarized abelian varieties is it's the quotient of this Siegel upper half space, which is a rather concrete object, by the action of the symplectic group. And the symplectic group acts on the Siegel upper half space by a kind of linear fractional transformation. So this was all in Anna's talk. So this is the object, AG. We want to think about here. And I said I want to think about cycles or cohomology classes. And the first source of cycles is from the Hodge bundle. So here we become now more specifically interested in the geometry of AG. So they're not now abstract objects. This Hodge bundle is a particular bundle, perhaps the most important bundle on this moduli space. And it's defined, in general, to define a bundle or an object in the moduli space. The nicest way is this kind of synthetic way, where it's a vector bundle. So I have to tell you over any object what the vector space is. And so here's an abelian variety. And the vector space of this Hodge bundle is you go to the 0. An abelian variety is a group, so it has a 0. You go to the 0, you take its tangent space, or actually the cotangent space. That's a rank. This is a space of dimension G. So this is a vector bundle of rank G. And this diagram defines it. And if you have one of these, then you automatically, in geometry, if you have a complex vector bundle, you get cohomology classes on the base, and those are the Chern classes that measure, roughly speaking, how twisted this bundle is. If this bundle were the trivial bundle, then these Chern classes would all vanish. If not, it measures somehow how twisted it is. Those are basic aspects in geometry, and these classes for AG are called the lambda classes. So if you just start with the study of this moduli space AG, you get, just from its intrinsic geometry, these G classes, lambda 1, lambda 2, all the way to lambda G. And these are the first objects of study. And they've been studied. So if you take this idea of not studying a particular AG, but the limit as G gets higher, then it's a theorem, a fundamental theorem of Borel, that says that this algebra is the free algebra on the odd Hodge classes, the odd Chern classes of the Hodge bundle. And this theorem is, in some sense, if you the much more recent progress on. So this theorem can be, in Borel's work, it's not written this way. It's rather the stable cohomology of the group, the symplectic group. If instead you consider the mapping class group, the parallel result was this Madsen-Weiss theorem, which was proven much more recently. So this is part of Borel's study of the cohomology of arithmetic groups. But it's a very nice result, and it says that stably all you see are these odd Chern classes. So you might think, what happened to the even ones? That's a reasonable question, and the answer is that you don't need them. There's a basic relation that says if you take the Hodge bundle plus its dual, then the total Chern class is 1. And there's various ways to see it, but it's roughly speaking, if you take the bundle plus its dual, it's flat. So it kills all of the Chern classes. And if you look at what this equation means, if you expand this fully, you will see that you don't need the even ones. You can use this equation to take the even ones out. The odd ones are all you need. And Borel's result says that, in fact, if you look at stably, the odd classes are free. Okay, so that's Borel, and that's a picture from the 70s. And if you've ever spent much time in Switzerland, you can see he has a very kind of distinctive Swiss style in this photograph. If you take Borel's result as motivation, then you can restrict your attention to this tautological algebra. So this is the algebra of the cycles on the moduli space of abelian varieties that are the simplest to think about. This was defined by Gerhard van der Heer in 1996. And in some sense, he took this motivation, Mumford's definition related to moduli space of curves, where there's a kind of a parallel issue going on there. But anyway, that's his definition, and it has this appealing idea that the Chow-Ringer classes on AG in general could be something that's very complicated to think about. But these classes are explicit and easier to think about. And OK, so that's the definition of this subalgebra. And the first question you can ask is, what is the structure of this algebra? And that just means that you have these generators. And I just put all of them in now. You have these generators, and the structure of this algebra on a basic level is what is the ideal of relations there. And this was solved in 1996 in the same paper where, in some sense, the definition was introduced. That's Gerhard van der Heer. And he just proves that the full ideal of relations are these Mumford relations, which I've already discussed, and just one more, that lambda g equals 0. So it's actually incredibly simple algebraic structure. And the proof is really nice. And if I had more time, I could give you the proof. But it uses something that's important, is that this algebra, if you consider it as a graded algebra, satisfies Poincare duality. And the reason for that is not it's not a surprise in some sense. If you know this algebra, you can recognize it as the algebra, the cohomology algebra of the Lagrangian Grassmannian. And there's a connection between this problem and the Lagrangian Grassmannian. It's kind of fundamental, and it's used here. So anyway, this is a line that goes to 1996, where you studied the stable cohomology. You can define the tautological part, and then you just solve it complete. That's the full algebra there. So you say, well, what are we supposed to do now? And so the very first question is, you could ask, are there some classes of algebraic cycles which are not tautological, which are not in this algebra generated by the lambda classes? And this question, in the context of the moduli space of curves, led to some important understanding of the structure of both tautological and non-tautological classes on the moduli space of curves. So it's a very reasonable question to ask here. And OK, so you have to think about some cycles that you could try to test, or maybe it may or may not be tautological. And a very simple cycle is a product cycle. So if I look at abelian varieties of dimension g1 plus g2, there's a subvariety or there's a cycle that's given by those abelian varieties that arise as a product of two abelian varieties of lesser dimension. Of course, g1, their dimensions add, and it is also the case if these two are principally polarized, then their direct sums, their product is also principally polarized. So this is a very natural map. It's a very naive way to make some cycles. In general, in moduli spaces, it's not an easy thing to make a lot of interesting cycles, or algebraic geometry in general. Writing cycles it's an interesting thing to write cycles. And so this is a very simple one. And you can ask, well, if you look at this thing, it reminds you of the boundary geometry of the moduli space of curves. If you have curves of two curves of genus G1 and G2, of course, you can connect them to get a nodal curve of genus G. And so one might think that it's reasonable to think about the moduli space of curves related to this question. So for the moduli space of curves, there's a very deep connection to abelian varieties that goes back to the beginning of algebraic geometry as a subject. Because if I have a curve, and here I have a curve of compact type, which I'll say a bit about in a moment. But if I have a curve to start with, a non-singular curve, I can associate to it its Jacobian. And the Jacobian is a principally polarized abelian variety. And if I start with a genus G curve, I get an abelian variety of dimension G. That's why the G's match here. That's why I chose G at the very, very beginning. And the twist here, if you have not thought about these things, is that I don't want to consider just smooth curves. I want to consider curves which are called compact type. And that just means that it can have nodes. But the graph, the dual graph of the curve has to be a tree. So there's no loops of components. And if I have such a curve, I can still associate to it. I can extend the Torelli map immediately to such curves because I just take the Jacobians on each component and look at their product. So that's a, and this, it turns out, this is this map is a better map to think about for the way I'm going to discuss the subject than just for smooth curves. It's because this map turns out to be proper. It's a technical term. Now, if you throw out the compact type curves, and you give yourself lots of holes, and then all the things fall out through the holes. So it's better to do this compact type. OK, and then if you want some technical definition, Jacobian is a multi-degree zero line bundles. OK, you can read it yourself. Actually, the Jacobian already came up in Mark's talk, so that was also. So I think that's more or less the way Mark wrote it. So the question then is that whenever we have a map, in fact, the Torelli map, as I said, takes compact type curves to the abelian varieties, you can always pull back algebraic cycles. And so the question now is whether this pullback map yields us any useful information about cycles, tautological or not. So that's kind of a question that will only be useful if you know something about the right-hand side. So to say more, we need to think about cycles on the moduli space of curves. So somehow we started with some naive questions about cycles on AG. And the tool I'm introducing here to address that is to study the Torelli map. And this tool is going to be useless unless you know something about where this lands. And what has happened in the last 10 years is that we really know a lot about where this lands. And so this tool is actually useful. I will explain. So this has to do with this direction of Pixton's conjectures and Pixton's relations on MGN bar. And this subject is on the order of 10 or slightly more than 10 years old now. And I am only going to give some kind of snapshot of this. So this is not the main point of this talk. But it's important because, as I said, that the only way this is going to be useful is if we know something here. And Pixton proposes for tautological cycles on MGN bar, he proposes a full set of relations. And those relations are explicit, meaning they can be put on a computer. And I just wanted to give some kind of understanding of the shape of those relations. So to get a relation, so that's this R, D, G, A, you have to give Aaron Pixton. So Aaron was a Clay Fellow some time ago. So that's a connection to the Clay Institute. So you have to give him a genus and n, which is completely reasonable because this relation is going to be on MGN bar. And then much less understandable is you also have to give him a string of numbers between 0 and 1. And I could explain that, but that's a different lecture. And you have to give a degree which says, roughly speaking, where this relation holds. And then the relation is that this object he constructs is 0. And then it's an explicit formula for this. And I said it's totally explicit. It's manipulated now, typically on computers because it's a complicated object. But the shape is that there's actually only two non-formal inputs. There are two of these essentially hypergeometric series, B0 and B1. And they're not unrelated. They're cousins of each other. And then you have to sum over all stable graphs. This is stable graphs with 5 elements. And the formula, his formula is if you want to calculate this fellow that's going to end up being 0, you sum over all of these graphs, and then there's some factor. And then if you have such a stable graph, it corresponds to some locus of stable curves, and you push forward some tautological cycles on this that have a familiar form in which you have to take some terms for the vertices, for the legs, the edges, and they're constructed in these functions. And the outcome is you get something that's 0. And the fact that this was 0 was proven twice, first in cohomology, that's easier to do. And then it was proven also in Chow by Felix Yanda soon after. So the part of Pixton's conjecture that's not a conjecture is that these relations that he wrote, they're all true. The part that is a conjecture is that about the completeness. So Mumford, in a famous paper in 1983, that's towards an enumerative geometry, the moduli space of curves, he opened the study of the algebra of these tautological classes. And Pixton's relations provide a first proposal, a complete proposal for their calculus. So it's parallel to the Schubert calculus for the Grassmannian, and somehow in the sense that Schubert calculus for the Grassmannian tells you you have some generators, and you can understand the complete set of relations in several ways. And this is exactly what Pixton proposes, that these relations are the complete set of relations among the tautological classes. So that's kind of a bold conjecture, and it hasn't been contradicted, but I would say that, well, there's a lot of room left to prove things. And how is this related to compact type? Well, compact type, these are some open subset of stable curves. So Pixton also conjectured already, I said more than a decade ago, that his relations, if you restrict them to compact type, you get the complete set of relations. So this gives us a tool to think about this Torelli pullback. If you have some cycles on AG, you can pull them back to the moduli space of curves. And if you're so lucky that your class is tautological, then you know exactly who is alive and who's not if you believe this conjecture. So that's roughly speaking the idea of the new idea to study this. So I said it's new in some sense because there's no way one could do this unless you have some idea of what's going on in compact type. OK, so let's try this. So we're going to pull back some cycles to the compact type curves. So first we look at the Hodge bundle. The Hodge bundle I defined at the beginning of this talk on AG. There's also a Hodge bundle on curves of compact type. And the way to think about that is if I have this curve, the g-dimensional vector space is the space of holomorphic differentials on that curve. And that's a g-dimensional, that's a rank G bundle. And of course, these definitions are compatible with Torelli. So you can check this. There's the Hodge bundle on AG. There's a Torelli map. And it pulls back to the Hodge bundle on MG compact type. OK, so then we have these Chern classes that the Hodge bundle has Chern classes just like on AG. And they're also called lambda classes. Of course, all this notation is supposed to match. So it's not a surprise these names are all the same. So the Chern class of the Hodge bundle on the moduli space of curves are also the lambda classes. And this Torelli respects the lambda classes. So if I define a subring of all the tautological classes on the moduli space of curves, which there are a lot because there's all these boundary strata, that there's a subring which is generated by just the lambda classes. Those are exactly the classes that come back, that are pulled back from Herard's tautological ring in abelian varieties. So there's the tautological ring of abelian varieties, and it maps to a small object, which is just the subring of tautological classes that's generated by the lambdas. So that's all correct. There's no discussion. So we can see, like, is this a condition to lie in this ring? So as an example in genus 5, the dimension of this ring of lambda classes in M5 is 11. And the full tautological ring is 66. I haven't defined the full tautological ring of the modular space of curves, but it's more or less you throw in all the classes you can name and all the strata, in particular the lambdas, the cotangent lines, boundary classes. So it's much bigger. You can see that in this genus 5, that's 66 dimensions, and to be somewhere that could possibly be in the image of the tautological classes from abelian varieties, only 11, so it's really small. It's a very small subspace, and so you could imagine this is some tool to test whether your classes are in the tautological ring. You can pull it back, and if your class falls outside of, if you take a class that's you don't know whether it's tautological and you pull it back, and it falls outside, for example, this 11-dimensional space, then it's definitely not tautological on the modular space of abelian varieties. So that's kind of a approach you can take. And so the simplest question in this line is to take the simplest product cycle. So I said we're going to think about product cycles. Take the simplest product cycle. It's a product of two people, one of whom is 1. So these are abelian varieties that have split off an elliptic curve factor. So it's a locus that's really easy to imagine here. And now we come to an actual geometric problem. I'd like to calculate the class, the cycle pullback of this locus under the Torelli map. That's something explicit. It definitely exists, and you have to try to calculate it. How are you going to calculate it? Well, we're going to do something before we do that. So we're going to ask, we'll calculate this class. We want to ask whether it's in this lambda subring. And before we do that, there's a little proposition, and it's a kind of a subjunctive. It's that if this were to be in this tautological ring, then we know ahead of time what it has to be. And it has to actually be, I mean, if it were to be in the tautological ring, then it would have to be a certain multiple of this lambda g. And it comes with the Bernoulli number, and there's a story about why this is true, which has to do with Hodge integrals. I'm not going to go into it now. And in fact, we wrote a proof in 2022, but this result was known in some sense to Karel Faber before. But this is a funny sentence. It says that if it were to be tautological, we don't know it is, but if it were, it has to be this. It can't be anything else. You can deduce that by somehow pure thought. So the fancy way to consider this is you look at this class, the products class, and you subtract the thing you know it would have to be if it were tautological. And then you get an obstruction that this class is in the subring if and only if, so if this class is in the subring, then this obstruction, when I pull back to the moduli curves, is 0. So you can go check this. Well, how do you check it? Well, you have to calculate this. This is a little bit hard work, but implicitly it's all in Fulton's intersection theory, that you have this morphism and you have the cycle. And the difficulty is that it's a painful excess calculation that took us months to do. But you have to study inside MG compact type the subscheme, which is the pullback of this locus. And that sounds like a simple question. So what happens is that it has many components, and they're bijective correspondence with partitions of G minus 1. And why is that? That's easy to see. So the components, so here is the dual graph. So when I draw this, red dot is a genus 1 component, and these AIs are components of genus AI. So you can see this thing, if the AI sum to G minus 1, this is a genus G curve. It's a curve of compact type. And if you look at its Jacobian, it'll have a genus 1 factor, so it will lie here. So these graphs give the irreducible components of this Torelli pullback. So in particular, this problem in genus G has partition number G minus 1 components. And what's worse is that so these components are almost always excess dimensional, and they intersect each other. So there's a big mess of intersection geometry. And then actually the hardest part of this is this issue about whether there are any nilpotents in that. That took a long time to understand. But anyway, this claim is that this Torelli inverse, a very explicit algebraic geometry. You pull back this cycle under Torelli, it's a reduced union of these components. OK, and so here's an example in genus 6. These are the top are the components. That's partitions of 5. And then these are the intersections and components and the intersections of intersections and components. And they all, if you actually understand excess intersection theory, you have to account for all of this stuff. And if you do it, you find that the formula for this pullback is the sum over all strata, these kind of strata. And for each one, there's a contribution. And it turns out that this contribution is always tautological. That's kind of good luck. So it means that this pullback class is effectively a tautological class. And you can really effectively calculate it as long as you do all this intersection theory correctly. So I tried to give one example in genus 6. It is equal to this combination, get some tautological classes. Anyway, it's totally explicit mathematics. So you're in a position to check whether this Torelli pullback is 0 or not. You can calculate this totally explicitly. And we have a proposal for all the relations here. And you can just see whether it works, whether it's 0 or not. And as I said, that everything is complicated, so all of the algebra is done on computers. And there's ADM Cycles is the computer package that's best suitable for these computations if you're interested. And I should say this is not artificial intelligence, it's all human intelligence. So if you do this, and as I said, it took us months to get this thing correct. And you're rewarded for getting it correct by showing that this obstruction vanishes. That's it's just 0 for 1, 2, 3, 4, and 5. This obstruction vanishes, and there's just no, I mean, yeah, when the obstruction vanishes, you learn nothing. And it's true that Pixton's relations are complete up to genus 5. So this is all somehow in the training part where we learn how to do this calculation. And for many of these, we knew that we knew this obstruction should vanish. But eventually, you learn how to do this correctly, and you're rewarded for being correct by getting 0 up to genus 5. And the first interesting case is genus 6. And as I said, in this question about whether we are two ships passing in the night, it could be predicted that the first interesting case is genus 6 by a connection to Langlands and work by Olivier Taïbi. And if you ask me, I can explain that now. But you can also predict this would be the first interesting case. Genus 6. So we have full knowledge of we now have full knowledge of this compact type. And why is that interesting? As I said, Pixton's only a conjecture. So Canning, Larson, and Schmidt just last year, and because of what I'm talking about now, proved the relations are complete for genus 6. And this is a kind of interesting direction in and of itself. And I want to say a little bit about it. And this is slightly technical, but it's kind of important here. So Karl Faber and I proved a long time ago for the compact type that there's one-dimensional space in codimension 2g minus 3, and higher than that is 0. And if you want to prove Pixton is correct, that his relations are complete, well, there's two steps. One, you have to prove that his relations are true, and that's been done. So you have to prove that anything that's not killed by his relations is not 0. And that's hard, because you have some cycles, and how do you prove that they're not 0? There was one idea to prove they're not 0, is that since we know this group is not 0, you can have there's a pairing, a bilinear pairing into that group. In genus 6, this 2g minus 3 is 9, and that's one dimension. There's a bilinear pairing here. And so if you can compute the rank of that pairing, it tells you some things are non-zero. And typically, you prove that Pixton's relations are complete by showing this is a perfect pairing, and that shows that everybody who you haven't killed is still alive. But what happens in genus 6, which is why it's the first interesting case, is that in codimension 5, genus 6, Pixton predicts this dimension is 72, but the corresponding rank has 71. So there's exactly one person there that is predicted by the relations to be not 0, but does not reveal themselves with the pairing. And so that means you need a different idea to show that person is not 0. And that's kind of complicated. That's the main result. And Sam Canning and Hannah Larson had introduced tools to study these low genus spaces very effectively. And you have to use all of that in ADM cycles. And I don't want to explain all of it. But they show that in this case, there's a right exact sequence. And this one we know is 988. And the image of this is 916. And the difference is 72. And Pixton was correct. So there is a one fellow there who is not 0, but is not revealed by this product. That's maybe the most interesting class. And this line of work is also interesting in its own right. It's the first case where Pixton's conjecture is proven without relying on the ranks of the pairing. So that was a little aside. But we need it because we need to know something about genus 6. OK, so then in genus 6, the statement is that this work does yield something. This, if I pull back the obstruction in genus 6, it's not 0. And as I said, we know this completely now. Yeah, by the way, this thing exactly lives in the place where it was most interesting. And we prove it's non-zero, and that proof is complete because you start with, as I said, the business about what happens here is conjectural, but the previous result I discussed by Canning, Larson, and Schmidt proved the conjecture is correct. So we have complete knowledge of this group. And we have this excess intersection theory gives us a complete calculation here. And then you can just, then it's linear algebra. You know the relations, you have this, is it 0 or not? And it's not 0. And so this gives the first cycle class. I mean, this was a fair amount of. Yes, exactly. That's exactly what I was saying. So the relevant pairing is that you have this 4, 5 to 9. And as I said, that there's 71 is the dimension of the 4, 72 is the dimension of the 5, we're in 5, and there's a one-dimensional kernel of pairing, and that's exactly our space. So this obstruction exactly reveals that one-dimensional pairing. And this is very interesting for us from other perspectives, which is that we want also to be able to prove Pixton's conjecture in general for compact type. And this is not a line I'm going to take up today. But it's a hope, maybe slightly wild, is that if we understand very well these types of cycles, that they can explain all of the people who are non-zero after Pixton's. But that's a different line. But this is kind of an amazing thing, that obstruction exactly picks up that little place where it's allowed to live. It lives there. OK, so that's the end of the first part of the talk. But you might think, what does this mean? Like, what is the so it does give an actual simple cycle, which is not in Hérard's tautological ring. And there was a lot of work to do that. But what is the meaning of it? So the first question for that is, what is the meaning of this, when I define this obstruction? Yeah, maybe the first question here is, what is the meaning of this? Can I say this more generally? What is this kind of subjunctive I was using here, and how to make that more general? So that's the next step, to understand what was really going on here with this obstruction. And that's a different paper. Oh, yeah, here. Yeah. OK, so we have to think about what that obstruction means. And it turns out that there's a really magical property about cycles on AG, which is not true for MG or moduli of K3 surfaces. And that has the existence of a projection operator. So this tautological subring that Hérard defined by the lambda classes is a subobject of all Chow cycles. It's just born a subobject. But compared to other moduli spaces, you have the thing that's different about AG is that there's a canonical projection operator. So it's also a quotient object. It's a direct summand. So this basically never happens. But here it's canonical, and the projection is defined via an integration map. And in this paper, the main result was a certain boundary vanishing of the top Schrödinger class of the Hodge bundle, which I'm not going to explain now. So if you want to understand this, you can ask me about it afterward on the board. But there is, for AG, there's this canonical splitting. If I have any cycle, I can project, and that's a tautological part. It's a projection, meaning if you do it twice, you get the identity. And so this gives a direct sum decomposition between, if I have, it's just saying what I said just with Gavin. If I have a cycle class, it has a tautological part, which is the projection, and then it has a purely non-tautological part. That's what you get when you have a projection. You get the two summands. And this purely non-tautological part, I've been mostly calling this shadow, which is, this is the subconscious Jungian shadow of the class. This is, Jung also lived in Zurich. So this class has this kind of two aspects, the tautological part, which is fully understandable, and its shadow, which is somehow lurking in the subconscious that we don't really have ways to name almost. And so then for any cycle, you can ask, what is its tautological part, and then what is the shadow? In particular, since we don't really have ways to name the shadow, it's a question about the shadow is whether it's 0 or not. And the class is tautological if and only if its shadow is 0. And so we can now you get it, and you get basically every cycle you want in AG, you can ask these two questions about. And in this talk so far, we've just considered the simplest cycle, A1 cross AG minus 1. But you can, for example, take any product cycle. This is a very modest generalization. So the first question you can ask is, well, what is the tautological part of this? That's the answer, that's the question about when we construct the obstruction. Anyway, the answer is this. It's in the paper. You can look at it if you want. If you take a product, abelian, this cycle of products in the L factors with these genera, its tautological projection must be somebody in the lambda algebra. And this is an explicit formula. So here's some product of, so there's a prefactor, which is a bunch of Bernoulli numbers. And then there's some lambdas, and then there's some kind of sure determinant. And this is telling you what the partition is. Okay, how can you prove such a thing? And as I said, the proof is on this path with the connection to the geometry of the Lagrangian Grassmannian, which is the compact dual here. And this path, at least from the point of view of complex geometry, usually goes under the name of the Herzebruch-Mumford proportionality principle. But anyway, it's not the topic of this lecture, but you can do explicit computations. And if you do that, you find, like for example, this is the tautological projection of our A1, AG minus 1 is exactly this guy. And it makes sense, because then you take the difference, that's about whether the non-tautological part is 0 or not. So this is the generalization of that subjunctive statement. You cannot take any class. You can compute, if you're lucky, explicitly its projection. And if you want to study whether it's tautological or not, it has to do with the difference. OK, so that gives you more or less, if you know cycles in AG, it gives you lots and lots of questions. You can answer, and again, you can answer, well, what is this about? What is the subject about? So in the talk so far, I've given you one class that has a non-zero shadow. That's just A1 times A5. That's a full calculation that shadow is not 0. But we expect many interesting cycles to have non-tautological parts. In particular, basically, if you pick random ones, they should also have interesting non-tautological parts. But it's difficult every time to show that. And there's many other cycles. These are really the most naive cycles. So if you want to be slightly less naive, although still very naive, you can consider Noether-Lefschetz loci. That's a beautiful class of examples. And the simplest of these are, you can look at principally polarized abelian varieties that have an elliptic curve. So something nonlinear elliptic curve inside that has degree d with respect to the polarization. So if this d is 1, then that's an elliptic factor. So otherwise, it's some kind of twisted version of it. There are Noether-Lefschetz loci. That language is usually used for K3 surfaces. So here maybe the Néron-Savary group of such a abelian variety is generically 2. So there's some kind of jumping in the number of line bundles. But this is just an example of a class. And we're going to study this now. But as I said, that you could pick anything you want. There's an article by Debar and Laszlo which classify all of these loci in AG which have Néron-Savary rank 2. And some of them are products, some are extensions, and then there's also some types of Shimura varieties involved there. But any one of those you could pick, and you can ask these questions. But I'm going to now, for the rest of the lecture, talk about these particular ones, because it's what we've been thinking about in the past year. So I just, to make sure that we're on the same page, because it's going to be about this, is that you fix your AG, and then there's for every d, there's a cycle. And the cycle is defined by having your abelian variety having an elliptic curve inside your variety that has, if I have this curve, I get a number which I can measure the degree of this polarization on that curve, and that number should be d. And as I said, if d is 1, you just get this product locus. So this gives for every genus, for every dimension here, this every g parameter, it gives me a nice countable family of cycles. I hope that's clear. Okay, so as I said, for the rest of the talk, I'm going to give some results and conjectures about this NLGD. And yeah, there's something kind of very interesting happening in the geometry of these cycles. So I should have said here, these cycles, so this cycle here is a codimension g-1 cycle. If g is 6, it's in 5, and all of these are the same codimension. This is a family of cycles, and they all have the same codimension, and that codimension is g-1. So they're not jumping around in dimension. They're all the same dimension. Okay, so the results and conjectures about NLGD. So as I said, the very first thing you can do if you find a cycle is compute its topological projection. This was done by a student of mine, Heitor Iribar-Lopez. So he was a master's student here at Oxford just a few years ago. So he computes it. And again, how he computes it, you can look. Actually, maybe his paper will appear on the archive soon. But I'm not going to discuss it. But he tells you if this d is 1, then I'd already written the answer down, because that's the product. And that d equals 1 makes all the red factors, these are the primes dividing d, all the red factors go away, and you get the old formula that I had written. But if you put the d, you get these extra terms. And you could say, well, what are these extra terms? So if you write these NL cycles in a slightly different basis. So you sum, so that's sigma 1, which is the sum of divisors, and you sum over all divisors of d, and you submit this to the sigma 1 function, sum of divisors. You get some kind of different linear combinations. This is a very common change of basis cycles. Then if you take Iribar-Lopez, Heitor's result, and you can consider it in this form. You take exactly this cycle, which is with a q parameter, and you take the topological projection of it, you get this Eisenstein series. Everything is times lambda g-1. So one of the things that comes out of this, I should have emphasized this is this countable family of cycles. And if you take the topological projection, a priori you could get some polynomials in lambda g here. You don't. You just always get a lambda g-1 and just a constant factor. And if you take the topological projection of this arrangement, you get this Eisenstein series times lambda g-1. Okay, so, and this is just, the calculation gives this. The Eisenstein series comes out. So it kind of shows that these cycles themselves have some modularity built into them. And this should remind you of a place where this happens, not in MG or AG, but in modular space of K3 surfaces. This is the kind of thing that the pattern that you see in Borchard's result about Noether-Lefschetz cycles on modular space of K3 surfaces. But Borchard's results don't apply here. Okay, so of course, if you see this formula, as I said, this d is defined for 1 to all integers greater or equal to 1. But if you see this formula, it's clear you should make the 0 one be that. So you can just define it. Okay, that's the first theorem. This is actually a theorem. But then you might think that this should make the connection between this theorem. In other words, this theorem is saying that this sequence of cycles is connected in some way to modular forms, SL2Z modular forms. And I want to make this richer and richer and more precise. And now we enter in the world where everything is conjecture. And the evidence for the conjecture is rather modest, but I'll try to say a little bit about that evidence. So I want to define the span of all of these cycles. So as I said, this is a countable number of cycles, even 0 because 0 was defined here, And for the higher d, it doesn't really matter whether you put a tilde or not, because this is just some kind of change of basis. So it's basically you just throw in all the cycles, all these NL cycles for a fixed g. There's a countable number of them. And that gives me some Q vector subspace inside here. So that's this NLG. And then there's the space of modular forms, the Q vector space of SL2Z modular forms. And this space here, NLG, is not explicit space. Who knows what that span is? But this is totally explicit. It's in the lambda modular forms. It's just given. It's a basis of monomials in E4 and E6 of the right degree. And so the first statement of the conjecture, there's going to be 3 statements. But the very first one was this pattern that Aaron proposed first. And then every time this data was presented in lectures, many other people found this pattern. But Aaron was the first one. Just the proposal is the dimension of this space, NLG, is the dimension of the modular space of the vector space of modular forms of weight 2g. So this should exactly match. And here I put g greater or equal to 2 for g equal to 1. You know, there's some mix of confusion and triviality in the definition, so we just throw that one away. It's because in in the one case, these things aren't really they're not the Lefschetz loci. There's no jumping of rank there. So that's there's some confusion there. Prefer not to think about it at the moment. But anyway, for all g greater than or equal to 2, this is a very precise conjecture telling you, it's not even clear that this span is finite dimensional. I mean, if I put cohomology here, then it'd be finite because cohomology itself is finite. But Chow, it's not even clear this is finite dimensional. But this proposal is saying not only is it finite dimensional, it's exactly the dimension of this modular forms of weight 2g. So I can give you some nature of the evidence for this, is that the space of modular forms of weight 2g, if I look at low g, the first time the dimension goes up is when g is equal to 6. 2g is 12, and you can make 12 as 6 plus 6 and 4 plus 4 plus 4. That's the first time it goes up. And that's supposed to be explained by the fact in M on this side that there's 2 elements there. There's the lambda g minus 1 and our A1 cross AG minus 1. So, and then there's more patterns like this that match. But anyway, that's just it's a conjecture. Now the second one, this was predicted in earlier work of Greer and Carl Leon, and the calculation of Heitor Ibarra-Lopez makes it precise what the weights are. So if you put the second conjecture, it says that if I take this cycle-valued series, that this is a Fourier expansion of an SL2 modular form of weight 2g with coefficients in the Chow group. So I just remind you that the evidence for this is that if I take that and I apply tau tot to it, then that's a linear function. If I apply it here, I get it. A Eisenstein series. So it's like some evidence for that second claim. So those are the 2 claims, and it's a little bit strange, these 2, because there's some modularity here which is about how much space these nodal Lefschetz cycles are taking, and there's a second modularity here which is about the Fourier expansions. And of course these can be put together, and this is my proposal to put these 2 together. So they kind of want to unite these 2 to make the 2 modularities somehow match. And so this is the third one, and for which there's the least evidence. The claim is that if I take the Q vector space, which is the span of these nodal Lefschetz cycles, that there is an isomorphism, a unique one, to the dual of the vector space of modular forms. So this isomorphism would mean that the dimensions are the same. And it satisfies this property. If I pick any modular form, that's on the left, I create its Fourier expansion by summing over Q, taking the cycle, applying this isomorphism, and then submitting it back to F. So some kind of tautological equation. So as I said, there's even less evidence for that. But it's the simplest explanation for these 2 things being true, which I said there's kind of weak evidence for it. And yeah, I should say that after we've been studying this for a year, you can see that you might think that, well, is this subject all about tautological classes? Already we know it's not about tautological classes, but more recently, Aitor has shown lots of things are not tautological. In fact, this is the biggest list. So I started this talk with just A1 cross A5 not being tautological. And now Aitor has proven for any D in 1 or 2, which is, there's infinitely many if that's just 1 or 2, and G equals 12 and all even G greater than 16, these are not tautological. So it's one of the reasons why it's a little hard to think about these conjectures explicitly, because these classes are somehow mysterious classes. We don't know how to, the way you'd want to think about this conjecture is you could just try to find a basis for the space and then just write formulas for each cycle in that basis, and you could see the modular forms. That would be the explicit way, but it's not really possible to do that. Okay, so that's I said, if you follow this very naive question that I started at the beginning of the lecture, eventually you get to some maybe slightly unexpected place where you're led to these questions about the modularity of these subspaces of nodal Lefschetz loci. And there are several other directions that are opened. I said one of them, was about trying to use the knowledge of these classes to generate all of the interesting non-vanishing related to Pixton's conjecture. And that's still somehow a pipe dream. We don't know how to do it. It certainly worked in that one case, but we don't know how to do it in general. But I wanted to finish with another connection, which is maybe a little surprising. Oh, that was the wrong way. Okay, so the last thing I wanted to talk about is that there's another connection which was found, which is also kind of mysterious. We understand it now, but when we found it, it was kind of mysterious. It's a long time. So there's the object, the Hilbert scheme of points in the plane. You think, what is this object doing in this lecture? But anyway, it comes. The Hilbert scheme of points in the plane, and you can consider the Gromov-Witten theory of this Hilbert scheme of points in the plane. And it's the Gina 0 Gromov-Witten theory was computed. I computed with Andre like 2 decades ago. And it's ruled by an operator of quantum multiplication by C1 of the tautological line bundle. So whatever it is, there's this space, it has some cohomology, and it has an operator of quantum multiplication. And this was generalized in many, many different directions by Devesh, Malik, and Oblomkov to AN singularities. And then Andre and Devesh also wrote a book on Nakajima quiver variety. So it's the beginning of a big, big story. If we're looking at the simplest case, and here we're looking at what's relevant to this talk is you can consider the genus 1 quantum cohomology. And the simplest series you can think about there is you take this Hilbert scheme as genus 1, and you have to submit some class in Gromov-Witten theory. And in the Nakajima basis, I submit this 2, which is just the 2 points of the Hilbert scheme come together. And we had found experimentally and eventually proven that the answer for this series is given by some kind of formula in terms of traces of that matrix that Andre and I found 2 decades ago. And so the question is, what is this doing in this talk today? And the answer is that actually that is connected directly to this calculation. It's in some sense, I would like to say it's logically equivalent to the calculation, but in fact there's a small gap in that statement it's logically equivalent, which is to say Aitor proves this calculation and we can prove that calculation, but there's slightly different methods, and the way we'd want to prove them is they're actually logically connected. But nevertheless, they're the same answer, and the connection is through a series of transformations in stable maps and stable sheaves. There's the Gromov-Witten descendant correspondence and Hodge integrals for elliptic curves, and finally Gromov-Witten the Lefschetz correspondence for this AG that was proven by Francois Grier and Lyon. And I said I would like to end with this slide because a long time ago when I was at Princeton and Devesh and I were working on, we wrote a paper on this Gromov-Witten the Lefschetz correspondence for the moduli of K3 surfaces, which tells you how to relate Borchard's results to calculating enumerative invariance for Calabi-Yau threefolds that are fibered in K3 surfaces. And I always thought then that there should be something like that for AG. And now, many years later, this is the thing that's like that. That here you're somehow, this is giving some kind of numerics about how this Noether-Lefschetz class is varying. And if you view this the correct way, it's actually computing this Gromov-Witten invariant of the Hilbert schema points. So that is the end of the lecture. And I wanted to put the pictures of the various people. That's Sam Canning, Hannah Larson, Sam Molho, Dragos Oprea, Aaron Pixton, Johannes Schmidt, Aitor Iribar Lopez, H.H. Tseng, Francois Greer, and Carl Lian. So those were all people who had worked. So that's all.